forgot what goals were. Hello, everybody. Think I'm audible. Yeah. Few announcements. Yeah. Yeah, midterm one. Can mute probably everyone. Okay. As I mentioned earlier, homework 4 or the homework related to chapter 4 has been split into more than one. In fact, I'm thinking of splitting it into 3 homeworks in principle. So there will be a homework 4B, which will involve only one lecture. That will be the Friday lecture, but I will give more time in the sense it will be due next week, so February 19th on Friday. And another section, homework C, I'll make it due on Monday. So that's so on Friday, that is the next lecture, I'll talk about whatever is needed in homework B, and the 2 lectures following the midterm, we'll talk about homework C. And coming to midterm 2, you should know where it will be available. It will be available in 3 places. One is it will arrive as an email. Second, it will be available on D2L under contents. And the third is it will be available on the course webpage. So whichever place you use most, that should be possible. I usually send the email first. All this happens within a few minutes before the midterm begins. I first send the email, then post it on D2L, and then on course webpage. And that is primarily so that I'm worried that if that webpage can take up all the 50 requests simultaneously. It should, but I just want to be safe in case it crashes or something. So that's about where the midterm will be available. And I also said the midterm will have 6 questions plus 4 conceptual questions, and how to prepare for it. So preparation is, let's say, homework, lecture examples, the lectures, and third is textbook examples. Like textbooks is pretty vast. There are lots of problems in there. So concentrate, if you want to prepare for the exam, concentrate on the examples, which involves reading the whole chapter. So you should be aware of the content in the chapter. That's what I mean. But it doesn't mean that you have to work out. I don't say the problems at the back of the textbook, because that's a pretty vast number of problems. Okay, with that, I'll get back to projectile motion. I want to work on specific examples. I spent about 2 lectures going over the concepts related to projectile motion. Even though we are talking about motion in 2 dimensions, we are mostly concentrating on projectile motion because it's very intuitive, and it's very common to see things around us which have a projectile motion. So let's specifically do some few examples which will clarify hopefully clarify the concepts. Any questions as such before I begin? Okay. So this is example on projectile motion. Let's say on projectile motion. Projectile motion, as we said, we launch a stone, let's say, and it goes up in the air and then comes back. And it doesn't have to be always starting from the ground and reaching the ground. That's only if it is very symmetric problem we talk about that, or let's say we throw a ball here and at what time or how far does it land. We can start from anywhere and anywhere on this trajectory, and let's do one of those examples. So let's say we begin from the very top. So we have let's say we begin from the very top, and how do you construct such a problem? Let's say there is something moving already in the horizontal direction, and an airplane is a good example. So let's say an airplane is traveling with a velocity v initial horizontally. So the projectile has not started, so we're just saying that there is an aeroplane that is going horizontally. Its velocity could be v initial, and since it is going in the x direction, let's say it's v initial in the x direction, and let me say that's specifically about 40 meters per second. An aircraft can go much faster than that. Remember, speed of sound is about 320 meters per second, and a fighter jet can actually go faster than that, and that is why we listen to shock waves whenever a fighter jet goes very close to you, faster than speed of sound. But let's say the purpose of this aircraft is to drop something. So first of all, it is flying very low and it is going very slow, so that whatever it has to drop, it doesn't come fall with too big a velocity, let's say. So 40 is significantly slower. Remember, again, if you want to convert it into miles per hour, approximately, you can multiply that by 2. So that's 80 miles per hour approximately. So that's your aircraft moving, and anything inside the aircraft is also moving with it at the same speed. Even if you're sitting inside that aircraft, even though you might think that you're at rest with respect to the aircraft, but you're inside the aircraft, so you're moving with that same velocity. So if you were to get disconnected from the aircraft, that means if you were to jump out of the aircraft, then you will be moving, you will already have a velocity of 40 meters per second. So that's a counterintuitive concept that you sometimes think that suppose you were to leave this aircraft, or you jump or you drop something from the aircraft, then its velocity should be just 0 and it will just fall vertically down. No, it actually has this horizontal velocity already, and you will go in this, so you will have a trajectory with an initial velocity of 40 meters per second. That's the same thing that happens with us on Earth. Even though we feel that we are at rest on Earth, but we are actually moving at a tremendous speed of about 4,000 meters per second around the sun, and we don't even feel it because everything around us is moving at the same rate. So we don't see we can only sense the difference in the motion. So due to that reason, we don't feel. So the main concept here is that whatever is inside the aircraft is also moving at 40 meters per second. And let's say you drop something from the aircraft, there's a package being dropped, so it won't fall naively. One would think that it will fall vertically down. No, it will not, because it has a horizontal component. So instead, it will take a trajectory like this. And you would like to know, like if you were the pilot of the aircraft and you're intending to drop a package at a certain point, then you would like to know how much before that should you drop it. You don't want to drop it right on top because then it will reach another place. So you want to drop it a little ahead of that. So for that purpose, you need to know how far this x distance, right? Let's call that x, or since we have we would like to use our parameters earlier, let's call that delta x. That means this point to this point. Let's say the height is given to us, so that's height h, and that could be your delta y. And let's say that's about 300 meters. This is what we would like to calculate. And that's all the information that is given to us, let's say, and we want to find out how far it will fall if you were to drop it at this point, horizontal distance delta x. So remember again that in the x direction, it is uniform velocity. So delta x, delta t, and v initial in the x direction. That's all there is. There are only 3 parameters in the problem in the x direction because it is going with uniform velocity. In the y direction, it is having 5 variables because that is delta y, delta t. It is now uniformly accelerating downward with 9.8 meters per second. So velocity changes. So there is a v initial in the y direction and v final in the y direction. And of course, there is acceleration, which is minus 9.8 meters per second squared. Let's try to see what other quantities given to us. This is, of course, what we want to calculate. That's our goal. V initial x is given to us. So this is your initial point, and that's your final point right before it hits the ground is your final point. And this initial component of the x component of velocity remains the same all through, right? Even when it is right at this point, it is still moving with initial velocity of 40 meters per second. So this diagram might be a little misleading. So it's actually having a slope there. It's not really vertically. So there's a slant that its vertical component might be very large, that the horizontal component will become very small, but nevertheless, it always has that horizontal component of 40 meters per second. So that's your 40 meters per second here. It's very clear that if we want to calculate delta x, we should find delta t. And for delta t, we go to the y direction because that's the coupling, right? That means to say we would like to calculate this. So let's notice that how the logic is going. You want to calculate delta x, but that requires delta t, but I don't have that. But delta t is common in both x and y direction. So you would like to calculate here. And in the y direction, since it is uniformly accelerating, we need to find 3. If we are given 3 quantities, then we can calculate any other quantity in there, or the rest of the 2 quantities in there. What are the quantities given in the y direction? Delta y is given to be 300 meters, but let's be careful. When we say this is minus 9.8 meters per second square, I have chosen my z direction to be, or the positive direction to be in the upward direction. So that's this makes it minus 300 meters. So that's a possible error, or relatively these two. If you choose this to be positive, that should also be positive. Otherwise, what I have been recommending is that choose a positive upward direction, and there is less amount of error possible. But we need 3 quantities here. If I want to proceed, I should have 3 quantities here, and it seems like we don't have a third information. No, there is an information here, and that comes from the concept that if it is horizontally moving, that means to say that when you drop something, even though it has a horizontal component of 40 meters per second, the vertical component is exactly 0. So even though it's not going to actually vertically fall, its vertical component of the velocity is exactly 0 right at that point. So this is equal to 0. It'll keep increasing. Yes, please.
I just have a quick question.
Yes, please.
Can you explain exactly why it's negative 300 meters for delta y?
Sure. It doesn't have to be negative. What I have been trying to emphasize is, I think I can use here. Okay. So let's draw again here. So that's your y direction. And this is a point here where you're beginning. So let's say this is 0. If I choose this to be 0, then this is clear that this is minus 300. If I choose this to be the positive direction, I don't have to. That's one possibility. The other possibility is that, oh, why should I choose my 0 there? So that's my 0. And then that's plus 300. But then how does that become negative 300? That might be your question. Remember, delta y is y final minus y initial. So y final is here, so that is 0. And minus of the initial, that's 300. That's one way of looking at it. So that's minus 300. Another possibility is that I choose this whole thing to be positive in the downward direction. And in that case, again, look at the trajectory here. So again, I can choose 0 here at 300, relatively speaking. If this was 300, that's, if this was positive, right? So this is 0, that's 300. If I choose this to be 0, then that's minus 300. Either way. But when I do the delta y, y final minus y initial, this will come out to be positive. So if you choose this to be positive, the other possibility is that you choose this to be positive. That's perfectly fine. But then this minus 9.8 also should change accordingly. This should be plus 9.8. Erase this part.
Okay, thank you.
Yeah, that's 9.8 meters per second square. And the velocity that if you were to calculate the velocity, this will come out to be positive if you were having positive here. It will come out to be negative if you use the negative numbers. Be consistent. I'm not forcing that you should use this way or that way. If you don't have a preference of your own, if you don't have any background where you have learned it in a certain way, then I suggest that always choose positive in the upward direction whenever possible, and it is less error prone. But if you're used to using this, that's perfectly fine. Don't change it. If you already learned a method, stick to that method. There's no need to learn another method unless you feel you're making mistakes. Okay, hopefully that helps.
Yes, thank you.
Yeah. Okay, so let me not use this. That's your okay. Coming back, so now we have entered all the quantities that's given to us. The important piece, which could be, which is conceptual, is this 0, like initial velocity, right when it leaves this is 0 in the y direction alone, not in the x direction. So that could be one thing you could have missed. From this point on, it's algebra, right? We see that, in the y direction, we have 3 information, so I can calculate delta t. So let me calculate that. So in the y direction, what is missing? So this is missing. So v final y is missing. So then my equation would be delta y is equal to v initial in the y direction times delta t plus half ay. So I just write a here because I haven't written y there, times delta t squared. Delta y is given, so remember that's minus 300. Plug in the numbers, that's 0 because the initial y is 0, plus half minus 9.8. I'm not writing the units, and that's delta t squared. Notice this negative sign always cancels that negative sign, at least whenever that square term comes in. If not for we being consistent with the signs, this will come with the opposite signs. And when you try to take the square root, it'll come out to be a square root of a negative number. So that's one other place that shows up. So let me move this down. Oops. Still make it visible a little more. Okay, so that gives me delta T is equal to 300 times 2 divided by 9.8. And then you take the square root of it. So that's 7.8 seconds. Notice that's a reasonably large time if you start counting 1, 2, 3. So it takes about 8 seconds for this package to fall from the aeroplane to the ground, and that's because it is it's 300. It has to fall this 300 meters. Once we have time, so that's delta T. So now we know 7.8. Yes, Christian.
You got 7.8 seconds?
Oh, did I not? Is that too much? Okay, 6. Okay, let's.
Wait, never mind. I just did something wrong on my part.
Okay, yeah, it is 7.8. For a change, I'm correct. Yeah, you always catch me. Okay, but thank you for looking for errors. Yeah, good. Okay, so that's 7.8 seconds. So that's 7.8 seconds here. That means it's the same time here, right? So that's 7.8. That's not given to us, but we have calculated it. That's what I mean by the boxed quantity. Once we know two quantities on the x direction, we can get the third one, and that's straightforward. So delta x is equal to the initial x times delta t. So that's equal to 40 times 7.8. Right. So 78 into 4 basically. So that's 312 meters. Let's keep it to 2 sig digits. So that's 310 meters. One can ask at this stage, just a concept part, that what will happen if this aeroplane was going faster? Let's say instead of 40 meters per second, it was going at 50 meters per second. There are two things you can ask. What happens to the time it takes for it to reach down? And second is, of course, how far does it go? Right? And the probably at least in the beginning, a little counterintuitive could be that this time doesn't change. If you were going faster, it is in the horizontal direction. Remember, horizontal and vertical are completely decoupled in a sense. And when you're calculating this delta t, that is the initial velocity does not enter into the calculation at all. It still is starting at 0 velocity. It is accelerating down at minus 9.8 meters per second square, and it has to travel the same distance, 300 meters per second. So this will stay the same even if you were to increase this to 50 meters per second. So that's one thing that might, when you first time realize it, it might be a little surprising or at least an interesting feature. And once you have the time, the delta x, of course, how far it goes horizontally does depend on this velocity. So if this is 50, then this will increase further. So by about 25%, so you will add 78 to that. So that's about 390 meters. So that's a good point to see. Any questions on that? Yes.
So wait, even though it was just 3 digits for the final answer, you still need to round to the number of significant digits?
Yeah, notice that, okay, the best way to do this is that use scientific notation. So usually the notation is that if there is a 0 following, if there is no decimal point and there is a 0 following the digits, then it's not significant. So it's understood that it's only 2 sig digits. But if there is any confusion, the best is to write it in scientific notation. So in
Well-
scientific notation, this will be 10 raised to 2. In that way, there is no confusion. There's 2 sig digits. There is no other way of writing it. So there's a clear, there is no ambiguity as to how many sig digits are there. In this also, there is not much of an ambiguity, but that involves a notation there that, okay, 0 following the digits is not significant. Does that help?
Well, what I was asking is that why do we need to round 312 in the first place?
Oh, because notice that there is this 9.8 sitting here, right? There's only 2 sig digits. So I don't know where, maybe in the place where this was falling, this could have been 9.84, right? So there is an error there in the third digit, right? Who knows? Maybe it was 8.4, it was 8.1, maybe it was 9.76. I don't know. The 2 sig digits tells me that I don't have any information about the third digit. Right? There's an error in the third digit, that's what it means. So that error will carry through in all this calculation, and it will most probably show up here. So it's a good practice to drop the third sig digit. I'm not very strict about that if it comes to exam, whether it is 2 or 3 sig digits. If you think the answer should have 2 sig digits and or if I think the answer should have 2 sig digits and you wrote 3 sig digits, I may not be very picky on it. But if you write 7 sig digits here, I won't like that. So I might take away a little point in there. Except when in the first chapter, there are specific problems where we ask significant digits. There you have to be very clear of how much, that is a very unique way of doing it. There also, if you notice, there was slight ambiguity as to is it 2 or 3 if you don't stick to the error analysis in the technical way. Did I answer your question?
Yeah, thank you.
Okay. Any other questions at this stage before I go to the next problem?
There is a question in the chat.
Oh.
It's just asking if you're going to upload the solutions for homework 4.
Correct. I will upload the homework on solution for homework 4. I tried to do it before the previous class, but I'm a little late. So today, before end of today. Yeah. So that will still give you about 24 hours to cross-check if you have attempted on it, cross-check. Does that clarify? Okay. And I also use, this homework solution is helping in a sense that I'm giving a lot of explanation while I'm making a solution. It's not just a solution as such. So that also I kind of clarify some point. It doesn't mean that that's a requirement that you go through the solution completely, but I think it helps in the sense that there are more examples being covered. In the lecture, I get to cover only about few examples, maybe 5 examples per chapter. In the homework, I get to cover more examples and I get to explain them also. So I think it is, or at least I feel that it should be useful resource there. But if you are confident about what's going on, then you don't have to look into it. Helps? Okay, so let's do one more example. So 20 minutes, so hopefully. So this is a usually the problem that I just now finished that is very symmetric. I still pick the top part and reach the bottom part, right? So often there is a slightly harder problem you can build on slightly, but logically speaking, it's exactly the same. I mean, it might have a little more algebra, that's all. So let's see what this is. So let's have a baseball, what would you say, baseball court or baseball stadium, let's say, yeah. And the batter is somewhere here and the ball is hit from a certain height. Since the ball is not really hit from the ground, it is at a certain height. So everything is shifted a little. So the ball starts from here. And this height is about the height of the shoulder of a person or the arm of a person, right? If an average person or a person with an average height would correspond to this about 1.2 meters. So already there is a ground, and the actual motion begins at 1.2 meters. The ball is hit, and it is the question is, does it actually clear a fence that is somewhere down here? So let's say there is a fence here that is 10 meters high. So that's 10 meters. But it is not necessary that this needs to be the best path. It is also possible that it goes like this, or it could go somewhere else, or it could go just like this. That's also possible. Of course, it will hit the ground here, right? But our equations doesn't know that, and it might go anywhere. So the question is, does this, if you're given the initial velocities, does this clear the fence or not? And the fence is 10 meters high, and it is 100 meters away. And that dot means that it is known to 3 sig digits. Usually it is easy to calculate the initial velocities. Let's say it is hit with 30 meters per second, and it is hit at 45 degrees. Since we have this magnitude and direction given, we can get the initial component of x and initial component of x component of velocity and y component of velocity. So v initial in the x direction is 30 times cosine 45, and v initial in the y direction is 30 times sine 45. Cosine 45 and sine 45 are the same, so that will be the same numbers. That's because it is at exactly at 45 degrees. So cosine 45 times 30, and that's about 21.2. So let me stick to 2 sig digits here. So 21 meters per second, and that's 21 meters per second. So that's some information we have. So let me put this all together. Let me collect the information. So that's delta x, delta t, and v initial in the x direction. We know delta x to be 100. That's positive, so 100 3 sig digits meters. Delta t, I don't know how much time it takes. V initial x is 21, right? And it is in the positive direction, so that's plus 21 meters per second. This is also positive if you want. Okay. In the y direction, we have delta y. Even though delta y is given to be, there is some distance of 10 meters given to us, that's not really the point. We want to find out what is the y when the ball is here. So we are interested in this height, which is not the 10. After we get that height, we have to analyze. If this number is larger than 10, then it crosses the fence. If it is less than 10, that does not cross the fence. So in principle, that delta 10 is not relevant. And remember that this motion begins on this dotted line here, right? So our delta y will be here. And that's still 1.2. Hopefully that's clear. So that's 1.2 meters. How much ever it goes above that is delta y. It doesn't have to go above. If it was this trajectory, here it will be negative. So whatever that number is. So first let's, that will be our target. That's what we want to calculate. Delta t is going to be the same as this. V initial in the y direction, we know, is 21. It is 21 in the upward direction because if we choose our our distances to be positive in the upward direction. That's plus 21 meters per second. We final in the y direction. That will be the velocity at this point. We don't know that. And acceleration is minus 9.8 meters per second squared. Clearly, we have only two information. We cannot calculate, we cannot work in the y direction immediately, but it is clear that we can calculate delta t here. Take it in there, then we have three information, calculate delta y. So that's our strategy. Let me move this out so that I have more space. So it is sort of the opposite of what we did in the last problem. In the last problem, we calculated delta t from the y direction and used it in the x direction. Here we do the opposite. Since we have two information available in the x, calculate delta t from the x direction, take it to the y direction and calculate delta y. So let's do that. So delta x is equal to the initial x times delta t. So delta x is 100 meters is equal to the initial, so that's 21 times delta t. So delta t gives me oops. Yeah. So delta t would be, that's 4.76. I can make it 4.8, but let me keep 3 sig digits here. Because when I take it there, there's going to be a squared quantity there. I feel the error is, it's a little sensitive for this third digit. So let's keep it here. But again, it doesn't matter. If you keep it 4.8, it should, the error should take care of itself. So there is a propagation of error, but that's the whole point, that we should be able to cover the extreme parts of the error. So time is 4.76 seconds. It's okay if you write for 4.8 here. That's perfectly fine. Once we have that, we know that delta t here is 4.76 seconds. I box that so that that's a temporarily calculated number. It was not given to us. And that's the same time in here. That's the time it will take for this ball to go from here all the way here, or wherever, whenever it crosses the area of the fence. We have three information here. We want to calculate delta y. The final velocity is the missing quantity. So delta y is equal to the initial y times delta t plus half a delta t squared. So that's the equation we would use, and that's equal to the initial y is 21 plus 21 times 4.76. That will be the same as, like, that's like 21 times 4.76, that should be 100, right? And plus half of minus 9.8 times delta t squared, which is 4.76 squared. We are not going out of the, oops, out of the. So this is plus half minus 9.8, 4.76 squared. Okay, and that's equal to square times 4.9. Right. So that's 111.0 minus, so it's minus 11.0 if you want, but 2 sig digits says minus 11 meters. Okay, that's, first of all, it's a negative 11 meters, so a lot of information in here, and it is measured with respect to this reference line where it was shot from. So where is the ball actually? It's not somewhere there. It is actually down here, right? Somewhere down there. And this height has been calculated to be minus 11 meters. So will it hit the will it clear the fence? No, it will not clear the fence. And this height is not relevant because before it reaches here, it will reach the ground. So a more practical question to ask is how far does it go? Right? What is this distance here? And you can do that calculation. But one could actually ask, what should be the speed with which you should actually shoot the or hit the ball so that it actually barely clears that. So that's another question one could ask, and I can sketch the arguments for that. So if we were to ask what should be the speed with which we should hit the ball so that it actually clears it, then we have to go back and change our v initial x itself and go in there. So remember your delta x, delta t, and v initial x. This is v initial now. This is a question we are asking as to what is this, and this is cosine 45 still. Delta t is not known. This remains 100. And in the y direction, delta y is now known because we want to barely clear it. So it is plus, not plus 10. So this is plus 10, which is given to us minus 1.2 meters. Clarify that. So, it's 8.8 meters. That's delta y. Delta t we don't know. V initial in the y direction. This will again be in terms of v initial times cosine 45. And we have v final y we don't know, and acceleration we know is minus 9.8 meters per second square. Since there is an unknown in the x direction and there is an unknown in the y direction, it seems like the strategy that we typically use doesn't completely go through. So what you have to do is that pretend as if this is given to you, calculate delta t. So temporarily calculate delta t, but you won't be able to get a number here. This will be in terms of v initial. So that will be a variable that will show up in here. Put that in here. And when you, so here you notice that it seems like there are three quantities given, but it's not because there is v initial is missing that. So now there will be a delta t also, and use the equation that doesn't have v final y, and you will get a straightforward equation for v initial. So I will just proceed forward with that information so that I can do one more small example in here. Any questions before I proceed?
It's not really a question, but so I was just curious to see if we were to plug in 4.8 instead of 4.76, and I got negative 12 meters instead. So if I were to do that in an exam, would you take points off for that?
No, I will not. I will not. In fact, that is so that what it means is that whether you take 4.8 or in fact you can even go 4.9, right? Any answer between these numbers is okay, because this could be 4.7 to 4.8, right? Not 4.8 to 4. So this could be anywhere between 4.7 to 4.8. That's perfectly fine. That's because there is an error in 9.8, the third digit, that is an error. So any number that you get from 4.7 to 4.8 is perfectly fine. In fact, if by any chance anyone grades you wrong on that, then you should argue on that, and I will surely not take off points. But sometimes it does happen that when you're grading, you have you're going through things quickly, and you have this bias that this is the answer, and you might get things graded wrong. But do come back, and this is a very valid reason. And sometimes error does propagate into a bigger number, like in this case I was pointing out. So that's why I took 4.76. So don't worry about. In fact, maybe I should have started with 4.8 and emphasized that. Helps, clarifies?
Yes, thank you.
One more question.
Sure.
Can you explain how we get the delta y?
Oh, here, is this one?
Yes, sir.
What I did was, okay, that is 3. You can see this. Oh, you cannot see that. No, let me move that up. Right. So notice that I calculate delta t. Is that clear? Can I proceed from there?
Yes.
So once I have the 4.76 or 4.8 will be more appropriate because that's what naturally one would have put. Put it here 4.8 because it's the same time. And then you have 3 quantities, 1, 2, 3, and this is like one-dimensional motion. And once you have 3 quantities, look for what you're looking for, that's delta y, and that's the missing variable. That's what I've been trying to convey, is that then the strategy is clear at least. Once this is missing, look for your equations of motion and find an equation that does not have the final velocity, and that turns out to be this equation. And this equation, put in the numbers, everything that you know, delta y is not known. That's 21, 4.76, and this is minus 9.8. The signs are important in this, and that's square. And this comes out to be exactly 100. It won't be 100, so that's where that error comes. If you put in 4.8, it won't be 100. But you calculated it this way, so it better be 100. But that's how error propagates, right? You make an error and this becomes something other than 100. And put in this and it get a minus 11 meters. Does that help? Or was your question something else?
Yes.
You don't seem very satisfied.
No, it's all.
Okay, sure. Okay, so let me proceed. There's 3 more minutes. Let me at least frame the question. It's kind of good to at least point this out. Okay, the other. Since I won't be able to finish it, refer to the lecture notes that is posted. This example comes there. Most of these examples I try to take from there. Notice that you could be in a range, and let's say this is an abstract line, horizontal line, and you're shooting a target. So this is a bullseye, and you would like to hit the center of the bullseye, right? And what you would do is you would aim the gun down there. But now, if this distance is very far away, this also happens when you're throwing a dart in a game room or somewhere, and there the velocity is of course smaller and these distances are small. But in a shooting range, this could be very large, like this could be about 100 meters. And then it is more dramatic in the sense this bullet is really tiny, going very fast. And what happens is that this actually falls. The bullet is actually going to fall. And of course, you can ask, how much does it fall? That's a simple question you can ask. And it is very similar to the problem we discussed earlier about a package being dropped, right? If you say that the bullet is initially traveling, bullet can go very fast, actually much faster than a fighter jet, and it could be 600 or 800 meters per second. You might have heard stories. I mean, it's interesting if you're in a fighter jet and there is a bullet traveling right next to you, it is not hitting you. You could actually hold the bullet in a sense. Of course, it will be very hard. But if you're going at the same speed, it might just be at rest with respect to you. So, so bullets go very fast. So that's 800 meters per second, let's say. And but it's going to fall. And you can ask how much distance does it fall? In the package problem, the delta y was given to you and delta x was not given to you. So it's slightly opposite. But that's the first part of the question. if it does fall, of course, you're going to miss the bullseye. So you would like to aim at an angle so that it actually does hit the bullseye. So that will be a projectile motion there. And then the question comes, if you launch it at the same speed, 800 meters per second, then at what angle should you be targeting this to? And it will come out to be a very small number, and that should give you, it should be impressive, because that's the skill you need to have if you want to be really shooting a bullseye in a far distance. Same thing with darts also. The velocity is smaller, so you have to be much more precise, but there it is less dramatic, that's all. So I won't work on this. Probably I'll explain these things more when I'm working on the solution. Today evening or later in the evening, I'll work on it. And yeah, good luck. Whatever we cover as of now, that is what is going to be there in exam. The Friday content will not be there in the exam. Thank you and good luck.
So you weren't actually going to do the second part of that baseball problem then? That was just to demonstrate different possible.
I discussed the problem. I went ahead so that I can actually work on the other problems, or at least mention the other problem. We shouldn't say.
Okay.
Yeah, I didn't get time, so I was going a little slow. But I think the strategy remains the same. I wanted to stress on that. So hopefully it helps. Okay. Also follow up with the homework there. Explanations will be there. So hopefully that helps.
Okay. Thank you.
Answer to your question is, yeah, I did not do it because of time.
All right. Have a good night.
You too. Thank you.
You're welcome.
Okay.